Osmosis. So, a lot of you have heard of osmosis, but you might not exactly remember what osmosis is. Osmosis is the diffusion of water, and water will always move of areas of high water potential to areas of low water potential. And a lot of times, what you would see this with like osmosis is if thinking like tube of toothpaste, if we increase, I have a tube of toothpaste. Because you never know what you're going to eat for lunch one day, right? So when you increase pressure on one side of the toothpaste, the toothpaste is going to move to whatever side that is going away from pressure. So increase pressure, toothpaste moves. So when you increase pressure on one side of, a cell, water is going to move away from that pressure. And you also look at solute when you look at water potential is how much stuff is inside the cell versus how much stuff is outside the cell, which is going to change which way water is going to flow. Now, I know that doesn't make a whole lot of sense, so we're going to talk a little bit about what it is like mathematically. I also think that there is an excellent YouTube video, which I have as an ed puzzle for you guys as part of your homework, which is going to help explain water potential in a way that I can only hope to do so because um, math and me tend to have disagreements about how things should be worded, which means more coffee. Which is a good thing to have toothpaste because coffee will stain your teeth. Just saying. And yes, I have a toothbrush to go with my toothpaste, but I'm not going to pull that out. All right. So this is the formula for water potential. That little trident-like symbol is actually called psi. And as Bozeman Science likes to say, like Poseidon carried a trident, which kind of looks a little bit like that. So any Percy Jackson fans in the house, right? So water potential equals pressure potential plus solute potential. So when we think about water potential, we have to take in fact pressure and solute. So animal cells don't have cell walls, so they don't have that rigid structure that plants do. So their pressure potential is going to be zero. So when we're talking about cells, we're looking at solute potential for animal cells. Plant cells, we have to take into account for pressure potential. So water potential will equal pressure potential plus solute potential. And we also have to take a think about, where is water going to move? Water is going to move away from pressure. Okay, it doesn't like to be pressured, but it'll also move towards solute because your body, anybody, any cell wants to maintain some kind of equilibrium. You can flood a cell with too much water. It is possible to drink too much water. You will lyse your cells and you will die. There was when the Nintendo Wii first came out, I was still in high school to give you guys an idea about how old I am. But I don't look a day over 21. So this radio show held a game where it was called Hold Your Wii for a Wii. And if anybody's ever read any British literature or has been over to the United Kingdom, you know that Wii also stands for pee. So what these people were doing was they were drinking massive amounts of water, and the person who lasted the longest got the Wii. In other words, the person who didn't have to run to the bathroom first. So it got down to two people, and it was just like, all right, these tiny little cups of water aren't working. So they started giving them bigger cups of water. And this woman won. She held her Wii and she won a Wii, but she died because she essentially drowned all of her cells. They lysed and exploded, and it was probably not a very pleasant way to go. You can also dehydrate cells. And if do not do this, it's absolutely 110% terrible. It's cruel. It's a horrible thing to do. But we all, like, not that we all know, but if you pour salt onto a slug, you'll kill it because salt is a solute. And that solute will pull all of the water out of the slug, dehydrate it, mummify it, and kill it. So again, we're trying to figure out where's water going to go. Is it going to go towards solutes? Yes, because it wants to maintain some kind of equilibrium. Is it going to move away from pressure? Yes, because it's going to try to maintain some kind of equilibrium. So we are chasing equilibrium here. So I said I wouldn't go through questions, but in this case, I am going to go through a couple of them here. So an animal cell with a solute potential of -3 megapascals is placed in a sucrose solution with a solute potential of -55 megapascals. What's the net direction of osmosis? So if this is my animal cell and it's got -30 or -0.30, I should say, and this outside solution out here is -0.55, okay, where is the water going to move? So where is the net direction of osmosis? So take like a little bit, okay? Take a second, like think about it. Is it going to move towards the cell? Is it going to move away from the cell, or is there not enough information? I can tell you right now, that's not an answer. The water potential is going to move where there is more solute. It's going to move outside of the cell because 0.55 is greater than 0.30. All right, so a fungal cell with a solute potential of a -2.5 bars is placed in a saline solution with a potential of -1.2 bars. So here's my cell. It's -2.5 bars. It's in a solution of -1.2 bar. Where is the net direction of osmosis? So is it moving into the cell or is it moving out of the cell? Okay. Where is it going to go? Also not an answer. Think about it. Pause the video. Work with me here. 2.5 is greater than 1.2. The water will move into the cell. Okay, so I'm going to pause the video here because I think I've been talking for a little bit, and this is actually a calculation question, which we'll review in the next set. So I didn't get too far in terms of slides, but hopefully this helped break things down and give you a little bit more information.